Black holes obey the same fundamental rules as something as ordinary as a cup of coffee slowly cooling on your table. That may sound impossible at first, but it is exactly what modern physics reveals. There are 4 laws of thermodynamics that govern everything from engines to refrigerators to the cells inside your body, and black holes follow all of them without exception. Not loosely, not approximately, but with exact mathematical precision. When scientists realized this, it opened one of the deepest doors in physics, connecting gravity with quantum mechanics in a way no one expected. This story begins in the early 1970s at Stanford University. I was a young professor at the time, still energized by the recent breakthroughs in string theory, and black holes were one of the hottest topics in physics. Back then, the accepted idea was simple and very strict. A black hole is a region of space where gravity is so strong that nothing can escape, not even light. Once something crosses the event horizon, it is gone forever. No return, no signal, no information. Because nothing could come out, scientists believed black holes had no temperature at all. They were considered the coldest possible objects in the universe, sitting at absolute zero. It made intuitive sense. If nothing flows in or out, there is no exchange of energy, no movement, and no heat. To explain it in a simple way, think of a pipe that only allows water in but never lets it out. Eventually, everything becomes static. That was how physicists imagined black holes, as dead ends in space-time where physics essentially stopped doing anything interesting. At the same time, a young graduate student at Princeton named Jacob Bekenstein was studying under John Wheeler, the scientist who actually introduced the term black hole. Bekenstein had an idea that seemed almost uncomfortable to many experts. He proposed that black holes should have entropy. At first, this sounded wrong. Entropy is a concept that measures how much information about a system is hidden from us. For example, when you look at a cup of hot coffee, you can measure its temperature, but you cannot track every molecule inside it. Those molecules can be arranged in an enormous number of different ways while still looking like the same cup of coffee to you. The number of possible hidden arrangements is what we call entropy. Bekenstein suggested that black holes also have this property, not as a metaphor, but as a real physical feature. Even more surprising, he claimed that the entropy of a black hole is proportional to the surface area of its event horizon, not its volume. This was completely unexpected because in normal physics, entropy always scales with volume. His idea implied something radical. Everything that falls into a black hole, whether it is a star, a planet, or even complex information, does not disappear completely. Instead, it becomes encoded on the surface of the event horizon itself. This idea was not easily accepted. It challenged the way physicists understood both gravity and thermodynamics. But it would soon collide with one of the greatest breakthroughs in theoretical physics. To understand why Bekenstein's idea created such tension in the scientific community, we need to look at what physicists already knew about black holes in the 1960s and early 1970s. Using Einstein's general relativity, researchers like Roger Penrose showed that when a black hole forms, its event horizon behaves in a very unusual way. Once it forms, the area of the horizon never decreases. This was not a guess. It was proven mathematically. No matter what you throw into a black hole, whether matter or even another black hole, the total surface area of the event horizon only increases or stays the same. It never goes down. Later, Stephen Hawking took this further and formalized it into what is known as the area theorem. He was quite proud of this result, and understandably so. It was a major insight into the behavior of extreme gravity. But this result created a strange comparison. In thermodynamics, there is also a law that says entropy in a closed system never decreases. That is the second law of thermodynamics, one of the most fundamental rules in physics. Now there was a problem. Black hole area always increases, and entropy always increases. The similarity was too precise to ignore. In 1973, James Bardeen, Brandon Carter, and Stephen Hawking published a landmark paper describing what they called the 4 laws of black hole mechanics. What they discovered was far more than a coincidence. Black holes obeyed laws that looked almost identical to the laws of thermodynamics. The first law connects changes in energy to changes in other properties like mass, charge, and rotation, just like thermodynamics connects energy changes to temperature and entropy. The second law, as already mentioned, states that entropy never decreases, and black hole area behaves exactly the same way. The third law states that absolute zero temperature cannot be reached in a finite number of steps, and similarly, a black hole cannot reach zero surface gravity. Even the zeroth law matches. In thermodynamics, systems in equilibrium have uniform temperature. For black holes, surface gravity is uniform across the event horizon. Mathematically, the structure was identical. Temperature corresponded to surface gravity, entropy corresponded to area, and energy corresponded to mass. Everything aligned perfectly. But there was a problem. Hawking and others insisted this was only a mathematical analogy. They believed black holes did not actually have temperature or entropy. If they did, they would have to emit radiation, and everyone knew black holes do not emit anything. Stephen Hawking was especially firm about this point. In his view, Bekenstein's idea was elegant, but physically incorrect. Black holes, he argued, were still cold and silent. Ironically, this belief would soon be overturned by Hawking himself. Part 3. In 1974, Stephen Hawking set out to prove that black holes had no real temperature. His goal was to demonstrate that Bekenstein's entropy idea was only a mathematical trick with no physical meaning. To do this, he applied quantum field theory to the curved spacetime around a black hole, a highly complex calculation that required combining general relativity with quantum mechanics. But the result he obtained changed everything. Instead of proving black holes were cold, Hawking discovered that they actually emit radiation. This radiation is now called Hawking radiation, and it showed that black holes are not completely black after all. They slowly emit particles, and this emission has a precise thermal spectrum. This was shocking. The radiation behaves exactly like heat emitted by a warm object. In other words, black holes have temperature. To understand this, we need to look at quantum physics. In empty space, particle pairs constantly appear and disappear. These are called virtual particles. Normally, they cancel each other out immediately. However, near the event horizon of a black hole, something different happens. One particle can fall into the black hole while the other escapes. The escaping particle becomes real, carrying energy away. The falling particle effectively reduces the black hole's mass. Over time, this causes the black hole to slowly lose energy. It is not eternal, it evaporates. Even more importantly, the radiation emitted has a perfect thermal spectrum, just like any object with temperature. This means black holes are not cold objects at all. They are thermal systems. Once Hawking calculated the temperature, something remarkable followed. The earlier analogy between black hole mechanics and thermodynamics suddenly became real. Bekenstein's entropy was not just a symbolic idea. It had a precise value. The entropy of a black hole is equal to 1/4 of the area of its event horizon, measured in fundamental quantum units. This result confirmed that black holes store information on their surface, not in their volume. This was a radical shift in understanding. It suggested that space itself behaves differently at a fundamental level than we previously thought. To grasp how strange this result truly is, imagine a room filled with objects. Normally, if you want to know how much information or stuff is inside, you measure its volume. A larger room contains more air, more objects, more possibilities. That is how entropy works in everyday physics. It scales with volume. But black holes do something completely different. Their entropy scales with surface area, not volume. It is as if everything inside the room is somehow written on the walls instead of existing within the space itself. This means all the information about anything that falls into a black hole becomes encoded on its boundary, the event horizon. This idea led to one of the most important developments in modern theoretical physics, the holographic principle. The idea suggests that our three-dimensional world might actually be described by information stored on a two-dimensional surface. In other words, what we perceive as depth and volume could be a projection of more fundamental data encoded on a boundary. This is not just philosophical speculation. The formula combining Bekenstein and Hawking's work includes all three major constants of physics: gravity, quantum mechanics, and the speed of light. It brings together the three pillars of modern physics into one equation. That alone suggests something deep is happening at the intersection of these theories. For many physicists, this is a signpost pointing toward a unified theory of everything, a framework where gravity and quantum mechanics are not separate but emerge from a single underlying principle. The discovery also triggered decades of debate. If black holes emit radiation and eventually evaporate, what happens to the information they contain? Does it disappear, or is it preserved in some form? Stephen Hawking initially argued that information is lost forever. Others, including myself, believe that this could not be true because quantum mechanics forbids information destruction. This disagreement became known as the black hole information paradox, one of the most important unsolved problems in physics. The deeper scientists looked, the clearer it became that black holes are not simple objects. They are thermodynamic systems with hidden complexity, and they may hold the key to understanding space-time itself. The debate over black hole information led to one of the longest and most intense discussions in theoretical physics. If a black hole evaporates completely through Hawking radiation, and that radiation appears random, then what happens to all the information about what fell inside it? Stephen Hawking initially argued that the information is lost forever. According to him, once the black hole disappears, the details of everything it absorbed are gone, replaced by featureless thermal radiation. But this created a serious problem. In quantum mechanics, information cannot simply disappear. It can be scrambled or hidden, but it must always exist in some form. If black holes truly destroy information, then quantum mechanics would need to be rewritten. This contradiction became known as the black hole information paradox. I disagreed with Hawking's conclusion. I believed that information must be preserved, even if it is extremely difficult to recover. This disagreement led to decades of research, debate, and new ideas such as black hole complementarity and holographic duality. Then something remarkable happened. In 1996, Andrew Strominger and Kamran Vafa made a breakthrough using string theory. They calculated the microscopic states of certain black holes and showed that the entropy predicted by Bekenstein and Hawking matches exactly with the number of underlying quantum states. This was the first time anyone had derived black hole entropy from fundamental principles. It confirmed that black hole entropy is not just a mathematical trick. It counts real microscopic configurations. The result was celebrated widely in the physics community. It showed that string theory could explain where black hole entropy comes from at the deepest level. It also reinforced the idea that black holes are not simple voids in space. They are complex quantum systems with internal structure, even if that structure is hidden from direct observation. This discovery pushed the field further toward the holographic principle and the idea that space-time itself might emerge from more fundamental information. Step by step, black holes stopped being seen as destructive endpoints and started being understood as windows into quantum gravity. Part 6. Today, the 4 laws of black hole thermodynamics continue to shape some of the most important research in physics. They are not just rules about exotic cosmic objects. They are guiding principles that connect gravity, quantum mechanics, and the structure of space-time itself. One major area of research is the information paradox. Physicists continue to investigate how information escapes from evaporating black holes. New ideas, such as black hole complementarity and quantum error correction, suggest that information is never truly lost, but instead encoded in subtle correlations within Hawking radiation. Another major development is the holographic principle. If entropy scales with area rather than volume, then the number of degrees of freedom in any region of space is fundamentally limited by its boundary. This suggests that our universe might be described by information encoded on a distant surface, projected into what we perceive as three-dimensional reality. This idea was made mathematically precise through the ADS CFT correspondence, which shows that a higher dimensional gravitational system can be equivalent to a lower dimensional quantum system without gravity. It is one of the deepest insights in modern theoretical physics. A third area of research focuses on quantum complexity. Even after a black hole reaches thermal equilibrium, its internal quantum state continues to evolve in a way that becomes increasingly complex over time. This has led to new ideas suggesting that complexity, not entropy alone, may be the key to understanding what happens inside black holes at late times. There is also ongoing work on cosmological horizons in our own universe. The universe itself, due to its expansion, has a horizon with temperature and entropy. This suggests that the same thermodynamic laws that apply to black holes may also apply to the cosmos as a whole. All of this traces back to a simple but revolutionary idea introduced by Jacob Bekenstein, that black holes have entropy proportional to their surface area. Combined with Stephen Hawking's discovery of black hole radiation, it reshaped our understanding of reality. In the end, what began as a debate about exotic objects in space revealed something far deeper. The same laws that govern something as ordinary as cooling coffee also govern the most extreme objects in the universe. This is what makes physics so powerful. It shows that nature does not change its rules depending on scale or environment. The same principles apply everywhere, from your kitchen to the edge of a black hole. Jacob Bekenstein's contribution was never fully recognized with a Nobel Prize, but his idea remains one of the most important in modern science. It continues to influence research today, long after his passing. And even now, as we push further into understanding quantum gravity, one thing remains clear: Black holes are not the end of physics. They are the beginning of something much deeper.